Professor, when we like have the project guidelines?
Yes, so the project, I can talk about this briefly. I mean, I'll tell you more about it towards the end of the quarter, but it's very open-ended. The idea that you choose some topic that is somehow related to this class. I mean, it could be something we discussed in class, but we haven't expanded on. It could be a paper that you want to read and sort of understand better. It could be like more high-level view of the field related to what we saw in this class, either to expanders or to high-dimensional expanders, and then just just speak with me before you choose a topic, and then the goal is that you basically write a survey on this topic, about, let's say 10 pages max, and again, it could be a more technical survey where you choose a paper and you read it, or it could be more like, a high-level survey where you choose an area, you do like a literature review of the area and you write about that. So it could be broad, it could be deep, it could be whatever you want. I mean, I'll suggest different topics as we get closer to the end of the quarter, but just off the top of my head, I mean, we've seen connection of expanders to various things like de-randomization, to correcting codes. So you can work more with that, or other applications of expanders, algebraic construction of expanders, random Zig-zag. Actually, we see one version of Zig-zag today, but the other versions, there were those. Or if you go to high-dimensional expanders, we're only going to cover very basic topics. I mean, there are many more topics that we won't cover here for the lack of time. So, and also applications. We'll see one application basically to mixing, to MCMC algorithms, but many other applications you can discuss. Could be application to quantum codes, could be application to what's called double samplers. I mean, agreement testers. I mean, there are many other applications that you won't cover here. So it's really very open-ended. I mean, so I mean, if you have some ideas, just maybe in office hours, you can just chat, and most topics will probably be okay. As long as they're somehow related to this class. And again, you can do it individually or in pairs. Again, it's up to you. Any more questions on the project? And I expect we're going to have 2 more homeworks and then the project. So that's it. Okay. Okay, so let's start with the Zig-zag. So my goal is that we can cover Zig-zag today, so we can start talking on high-dimensional expanders on Thursday. So what's the idea of Zig-zag? So it's a very different type of construction of a sparse expander. So our goal will be basically, again, to construct sparse expanders, right? And by sparse, I mean constant degree. So that is to be constant degree, and this will also be spectral expansion. This is easiest to analyze. But we've seen Shiger inequality connecting this to other notions of expansion, like edge expansion. And we've seen already sort of several types of construction. So the one we saw in the last couple of lectures was an algebraic construction, the Morgulis double Galil construction. Also in the homework, you saw basically an elementary construction based on small batch generators that has logarithmic degree. And today we'd like to show you a recursive construction called the Zig-zag construction that's going to give us constant degree. And one of the benefits of it is it's very flexible. So what we'll do today is to analyze spectral expansion, but you can use similar techniques to analyze other notions of expansion that are not directly related to spectral expansion, like for example, vertex expansion, or getting unique neighbors expansion, and things like that. So again, we won't cover it this lecture, but just be aware that you can use a Zig-zag because it's very flexible to get various other types of expanders. Okay, so what's the idea? So the idea that we want to do it, so we want an iterative construction or recursive. It's called iterative or recursive construction. So imagine that you already somehow were able to get some expanders. Maybe here's my expander. It has, it has n nodes. It has a degree is going to be D, and the expansion going to be lambda, which again is always going to refer in this class to spectral expansion, right? So I won't say spectral again. Whenever I say expansion, always going to mean spectral expansion. And the question is, what type of operations? So what operations? Okay, and the goal is somehow to expand it, right? The goal will be use it to get a larger expander. Maybe with not the same D and lambda ideally, but on more nodes. And before doing that, I want to see what kind of operations can we, what do we know about expanders to begin with? Well, we know that we can, for example, take like a very dense graph. You know, the dense graph is going to be a very good expander, right? If I have the, so if I have the complete graph, let's say, I don't know, GM, sorry, not GM, so it's KM, for the complete graph on M nodes, that's going to be an expander. So its degree is going to be big, M, but its lambda is going to be something like 1 over root M, right? So very small. So it's very, if I choose M to be bigger and bigger, I get lambda smaller and smaller, that's great, but then I pay the degree also gets bigger. So idea 1 is going to be sparsified, a dense expander. So we'll see some operation that starts with a dense graph that may be the very good expander and uses it to create a sparse graph that is also going to be a very good expander. Maybe slightly worse, but pretty good. And this is going to be the idea of Zig-zag that we're going to see more formally later. But before doing that, I also want to show you a second idea, which is so assume some graph G is, you know, deregular and lambda expander. And let's say for some reason I want a better expander. I want an expander with a smaller lambda. What can I do with a very simple idea, which is to take the square of this graph. So define, so this way. So let G square be the graph with the adjacency matrix G squared is just a G squared. So G squared basically corresponds to taking paths of length 2 in my original graph. So if my graph G had nodes U connected to V, connected to W, then in G squared, if this is in G, then in G squared, I'll just directly connect U and W. Okay, so basically G squared, we'll identify graphs with the adjacency matrices. So, and in general, we're going to allow for, you know, loops, we'll allow for multiple edges. So just think of the adjacency matrices as you know, matrices where the ij entry counts the number of edges to an ij, right? So squaring the adjacency matrix of a graph just creates the adjacency matrix of a new graph that corresponds to steps of size 2, right? Every single step in G squared corresponds to taking 2 steps in G. So what can we say about G squared? So I want to argue, well, first of all, if G was deregular, what's going to be the degree of G squared? Anybody? Like in G, every node they have D options of going to a neighbor. And G squared is formed by taking 2 steps. What's going to be its degree?
D squared.
D squared, exactly. D squared regular. Right, and again, think of these graphs as saying, from every node U, I have D options of going to V, and then from every V, I have D options of going to a neighbor, which could be U or a different. I mean, here I won't care about going back or not. So I have in total D squared options. In particular, G squared has like, you know, D self loops around U, right? So that's maybe not very good, but we don't care. I mean, that's going to hurt us, but we don't care what he thinks. But the benefit is, what can we say about the expansion? If G is a lambda expander, what is the expander of G squared? I claim that's going to be lambda squared. So we're going to improve the eigenvalue. Why? Well, it's very simple. But let's analyze this. So let F be orthogonal to 1. So we want to analyze, and maybe let's say the norm of F is 1. So remember that what we want to analyze for G squared is F transpose G squared. And actually, also here, I'll let me say sorry. See what I meant. Let's say put it the adjacency matrix. So the normalized adjacency matrix for G. Right, this is what we want to analyze to bound the eigenvalue gap for G squared. But what is this? Because F is orthogonal to 1, I'm claiming that's going to be, well, what is this? This is going to be, sorry, let me see what the easiest way to do that. So it's going to be the, let's write as F transpose AG F, right? AG is equal to its transpose, it's a symmetric graph. This is just a norm of AG F squared. Because F is orthogonal to 1, and this is smaller than lambda F squared, which is lambda. Sorry, lambda squared. Right, the idea is that since F is orthogonal to 1, we apply AG, it shrinks by a factor of lambda. It is still orthogonal to 1, we can do it again, it again shrinks by a factor of lambda, and so on. So in general, taking G to some high power, you know, we pay because the regularity increases, the degree increases, but the eigenvalues shrink. So basically what we're going to do is combine these two operations. So this zigzag operation that I haven't defined yet, it's going to take me a very dense but really good expander, and going to create with a sparse expander that's slightly worse. And then this squaring operation is going to slightly increase the degree, but going to really improve the eigenvalue. And by iterating these operations, we'll be able to get larger and larger graphs that are all going to be constant degree, constant expanders, but with more and more nodes. Okay, so that's going to be the high-level idea. Iterating these two operations. Okay, so now let's start seeing the details. Okay, so the first thing that we want to define before the zigzag is something like the precursor to the zigzag, which is called the replacement product. So the idea, so let me first write a definition, and then I'll show you some examples. So we're going to have two graphs. So let G be, let's do it this way. Let G, which is B1, B1, be a D-regular graph, or capital D. So think of this is a big thing. And then also we're going to have H. H is going to be a small graph on D2, be D-regular. Okay, so we're going to have two graphs. G is a big graph of which is degree capital D, and H is a small graph that has capital D nodes and its edges. What does it, and what's going to be the replacement product? So we're going to say the following thing. If in G, I'm going to define the replacement product in a second, but let's before I do that, let me show some pictures. So if this is G, if in G I have a node V, and this node V has some edges going out of it, out of them. Let's say it's 5. So we're going to arbitrarily going to number them 1, 2, 3, 4, 5. And we're going to 1, 2, 3, 4, 5. In the replacement product, we're going to replace it by basically 5 new nodes. So we're going to call them product that. So it's going to be 1, 2, 3, 4, 5. So I replace this 1 node with 5 nodes. And then I need somehow to connect them. And for this, I use H. So here in between them, I'm going to put whatever H does. So this is going to be H. H is going to be the red part. And that's going to be the replacement product. So for every node in the first graph G, we're going to replace its node with capital D new nodes corresponding to each edge going out of them. And we're going to interconnect these nodes using this graph capital H. Okay, so let's now write this formula. Okay, and then we see if you have any questions. So the replacement product like this: G R H is defined as follows. Is defined as follows. So its nodes are going to be all the pairs V, I, where V is a node in the vertices of G, and I is a number in 1 and capital D, like we did here. And what are going to be the edges? So the edges are going to have 2 types: inner edges between nodes of V and outer edges. So what are going to be the edges? There's going to have 2 types. We're going to have 2 types of edges. So the first type is going to be the inner red edges. So for every V in V1 and IJ in the edges of H, we're going to have the following edge: VI, VJ. We're going to have the edge VI, VJ. Right? This is now the name of an edge is a pair, VI or VJ, just a name, right? And now these are just the red edges above it. This is like the inner nodes of H. And also we want to make sure that we're still keeping the connection in G. So remember that every edge, we gave it a number. Like the edges in the V, if V is like 5 regular, we call them 1, 2, 3, 4, 5. Now, think about the other node here. Maybe this node here. Let's give it a different color. Let's say this is connected to the node U. Well, this edge is going to have some number going from U to V, which might not be 4. I mean, we're going to number these edges arbitrarily going from every node, so I won't even require that. If I call this edge 4 going from V, maybe it's going to call now 3 going from U. So you won't require any local consistency. It won't be important. I mean, you can assume it if you want, but it's not important, so we won't assume it. So the second type of edge is going to be the following. For every edge, let's call this maybe UV in the edges of G, if V is the ith neighbor of U and U is the jth neighbor of V, then what edge should we add here? Well, let's see. So the node that goes from V to U should be Vj, right? Because U is the jth neighbor of V. And here's going to be Ui. We're going to have this edge. So again, maybe now let's just sort of do a picture here. So maybe that's going to clarify this definition. So let's say, let's do an example. By the way, before the example, are there any questions on the definition here? I mean, maybe it shouldn't be, let me first do the example to to clarify maybe the definition, then we can see if you have any questions. So let's do an example. Let's say G is just going to be this square, just going to be this grid, the integer grid. Okay, so it's 4 regular. Let's say H is going to be the cycle, right? So there's a cycle of length 4. What's going to be the replacement product? Well, first of all, I take every node here and I replace it with 4 nodes, right? So it's going to look like that. One node, another node, another node, another node, and so on. And we're going to have 2 types of edges. We're going to have the inner edges that just connect these 4 nodes. So I replace each node with 4 nodes. And I'm going to have the outer edges do like that. Okay. So this is what we call the replacement product. Okay, so now let's see. Does anybody have any questions on this definition of the replacement product? No. Okay. So let's ask us some questions. So here's going to be question 1. So G is going to be deregular, and H, which again is well, you know, the nodes of H is D, is going to be some small deregular. What can you tell me about G replacement H? How regular it is?
Little d plus 1.
This one.
It's going to be exactly. It's going to be little d plus 1 regular. So you see, it inherits regularity from the small graph H. So even if capital D was very big, it doesn't care. So that's one thing. Now, what about the number of nodes? The nodes. What is the number of nodes in G and H? Well, every node in G I replace with capital D nodes, right? This cloud of capital D nodes. So that's going to be exactly the nodes of G times the nodes of H, right? Which again, reminds is just capital D. So we increased the size of the graph. We made it more sparse, like H, basically. So if this would be an expander, let's assume G is an expander, H is an expander. If this would also be an expander, we won't, right? We found that we have taken 2 expanders, combining them and getting another expander that's bigger and still pretty sparse compared to the sparsity of H, not of G. Unfortunately, that's not the case. So here's the fact. GRH is not an expander, even if G and H are expanders. So somehow this is a very nice product, but it doesn't maintain expansion, and let's see why. So again, let's draw this stuff with the picture. So sort of my replacement looks like that. Let's say this is a copy of H. Here's some connections coming from G. Why is this not an expander? Can somebody see why such a graph can never be an expander?
Is it because like the edges coming out of H are there's not a lot of edges coming out of H?
Yes, exactly. So if you look inside H, inside every copy of H, you're a really good expander because H is an expander. But going from H, one copy of H to another copy of H, there's very few edges. In fact, if you do the calculation, take a node here and ask, so let's take this H, let's take one copy of H. Almost all the edges go inside. From every node in a copy of H, exactly one edge goes outside. So if I set S to be some copy of H, then the number of edges going from S to outside S is exactly S. But the sum of the degrees, right, the sum of the degrees of the nodes in S is d plus 1 S. So we get expansion, so we get edge expansion, most 1 over d plus 1. So pretty poor, right? Very few edges go out. So while we got a sparse graph that's big, it's a poor expansion. It's poor expanded. So the question is, how can we fix this? So the idea of zigzag is to basically fix this by forcing you to always go outside H. So here the problem, every node, if you take like a random edge from it, most likely going to stay inside H. And only there's one option of going outside H. So what we'll do in the zigzag is force you to go outside H. We're taking multiple steps in this graph. So again, here good intuition. If you think about this G squared that we saw before, where we take 2 steps in the graph and it improves expansion. So here, this is gonna help us improve expansion by forcing it to go outside H. So it's gonna have some part that's random, but some part that's deterministic and forces you to go outside H. Okay, that's gonna be the idea of zigzag. So maybe now is a good time to stop for questions. Does anybody have any questions?
Wait, did you say that like, because I thought that this was like an explicit construction, but you said that some part of it is randomly
No,
constructed?
it's not random. Because nothing will be random. I mean, just think about the process of taking like you choose a node here and you choose like a random edge going out of it. So you want to, this is like what you get from the normalized, adjacency matrix.
Right.
So then here, most likely you're going to choose an edge inside H. And in the zigzag, we're going to force you to choose something outside H. Some reasonable
I see. Okay, that makes sense.
Yeah, but it's completely deterministic. Nothing is randomized here. Okay. So now maybe it's a good time to define the zigzag product. Now we're going to define the zigzag product. So again, what are going to be the ingredients? So G is going to have, it's a node P1, P1, that's capital D, regular. H is going to have capital D, small d regular. And let's also use GRH with the replacement product. So I'm going to define this by defining what is an edge. So when you go from an edge, that is one step in this graph. So again, the nodes, so the zigzag, we're going to denote by GZH for zigzag. But these nodes are going to be the same as the replacement. It's going to be I, P1, I, and D. Same nodes, but just more edges. So what are going to be the edges? So to define the edge, I tell you from every node, where can you go by an edge? So a node VI, so from node. So we're going to make 3 steps. Step 1, so you can go to a node VJ, where IJ is an edge of H. You make 1 step inside H. And then you remember every node VJ has exactly 1 edge going out of the copy of H to a neighboring copy of H. So assume Vj is adjacent to some Wk. There's exactly one node outside the cloud of H which is adjacent to. I'll show you a picture in a second. So go to Wk. And then step 3, you go to W, let's say L, where KL are in it. So what do we do here? So let's go, let me draw the same picture as above and show you what's, so again, let's take the same example as we did before. The edges, and we have the H edges. Now, what is the step here? So I start at a node. Let's say I start here. First, I go to a neighbor inside H. So if this is going to be my VI, first I'm going to choose Vj. So one of the D neighbors inside the local cloud of H. That's going to be the first step. Second step is this node has exactly one neighbor that is outside its local cloud of H. So I go here. I call this is going to be Wk. And then the last step is going to be go from Wk to again to one of its neighbors inside the local cloud of H. So maybe now it's going to go here. WL. So right, so we have this 1, 2, 3 steps. And anything that you can reach in this way, we're going to connect by an edge. So that's going to be an edge in the zigzag graph. So an edge in the zigzag graph corresponds to a 3-step process as I listed here. You take a local edge inside, so you take an edge in the local H cloud, you take deterministically, go to the one neighbor you have outside the local cloud of H, and then you take another step inside the local H cloud of the new node. Okay? So this is a definition of the zigzag product. And the claim that we're going to prove that this is in fact is going to be an expander. If you start from G and H, which are good enough expanders, the zigzag product is also going to be a good expander. Because it avoids exactly the problem that most of the edges are inside H. Because here now we're forcing the work to take a step from one copy of H to another copy of H. Okay. So maybe before we analyze, let me ask you a question. Let's just analyze the simple things first. What's the number of nodes here? How many nodes do I have here? This zigzag.
16.
What?
16.
No, not in this specific graph. I mean, like in general,
sorry.
we have G and H. And so so let's say, so assume, so we said, let's say G has n nodes and is d-regular, and H has d nodes, some capital D nodes, and is small d-regular. And maybe use different color. Actually, this is H. Let me put this with red. So H has capital D nodes. It is small d regular. What about the zigzag products? How many nodes does it have?
So we didn't add any when we did the zigzag, right? So it would be the same as when we got from the replacement product.
It's lunchtime.
Yes, true. So what is that? It's going to be
D times V of G.
yeah, n d nodes, right? It's going to be basically the number of nodes times the regularity of G. So it's the number of sort of direct edges in G. How regular is it going to be? Is it going to be depend on the regularity of G or the regularity of H? Well, let's see. How regular is it going to be? So let's count options. Given a node Vi here, how many options do I have? So step one, I go to one of its neighbors in H, and this has small d options, right? Small d. And then the second two has just one option, which is deterministic. And then the third one, again, has d options. So overall, this is going to be d squared. Do you see what we get here? The regularity of this zigzag just depends on the small graph H, while the number of nodes depend on the big graph G. But this gives the best of both worlds. If we put this in an expander, then we have a way of starting with the graph G that's pretty big to begin with, and maybe has large degree, but not too large, and putting on top of it this other graph H that has even smaller degree, connecting them by this zigzag product, and getting a larger graph, which is again small degrees. So the only thing we sorry what?
I was wondering, do we not include the original edges?
No, we don't. We don't.
Okay.
Just, I mean, you can make variations, and then most of them are going to work, but this one is the one that's easiest.
Okay. Okay.
I'm sure other variations could also work, but this one is easy to define, easy to work with. So the main theorem that I want to tell you about is the following theorem, which is called the zigzag theorem. This was proved by Reingold, Badan, and Wigderson. And it says the following thing. It tells you that if G and H are expanders, then the zigzag product is also a pretty good expander. So it says, let G be a irregular alpha expander, and H be a D-node small irregular beta expander. Then GZH is also an expander, is a, and 1 second, let's call this phi alpha beta. Phi alpha beta expander. So something just depends on the expansion of G and H, and we'll prove you can prove various things about these things. Like for example, phi alpha beta is at most alpha plus beta. So if alpha and beta are small, it's also small. You can prove that if alpha and beta are both below 1, then phi alpha beta is also below 1. So if both alpha and beta are expanders, it's also an expander. And you can prove more things, but for now, maybe that's enough. So you can prove even more properties of it. And we'll prove something slightly weaker than 1, which is still good enough to prove expansion. So again, the way you want to think about it is that, well, number 2 says if G and H are expanders, so this is going to be an expander. And number 1 says, well, if I know something pretty good to begin with on the expansion of G and H, I can get something pretty good on the expansion of the zigzag product. Okay. So before proving this theorem, I want to show you how we can use this theorem to build recursively sequence of expanders that we have the same degree, same expansion, but more and more nodes. And then the last thing we look at is prove the theorem. So now what we want to do is we want to, so what's it going to be? So we're going to have a recursive constructions of expanders using the theorem. So as a base case, what we need is something that seems simple, but I'll tell you what it is. So what's going to be the base case? We will need a graph H that has with d to the 4 nodes, d regular, and 1/4 expand. So we need this as a base case. You can ask, well, how can we start with that? Well, there are many ways you can get this H. First of all, by you can just have a random graph. If small d is a large enough constant, it's going to satisfy this high probability. Because this is a pretty dense graph, right? The degree is polynomial in the number of nodes. And actually, we've seen constructions. If you remember, if you see constructions even in the homework, we had log degree and pretty simple constructions. So once you choose a degree small d large enough, then d is more than log of d to the 4, right? Or you can use algebraic constructions or random constructions, or you can do various things. It doesn't matter how you start, but you start with some base graph, and again, you should think here about d is some constant that's big enough so you can get this to work. And there are various ways you can get this to work. So you start from one of these graphs, and you want to start blowing it up. So what's going to be the construction? So the first graph is just going to be h squared. So we start with h, and remember, squaring the graph increases the regularity to square, but also improves expansion by square. And then if I constructed g1 up to gn, gn plus 1, recursively is going to be the following thing. I take the n graph, I square it, and I zigzag it with h. Okay, that's going to be the construction. So you see what we do here is we alternate these operations. We square the graph to improve its expansion, but then we pay in the degree, and we zigzag to reduce the degree and slightly pay in the expansion. But overall, we gain. So let me now show you the calculation why this works, and this will just follow from basically the zigzag theorem. And then we're going to spend the rest of the class to just prove the zigzag theorem. So what's going to be the dilemma here? It says that Gn is a d-square regular half expander with d to the power 4n. So the number of nodes is going to increase exponentially fast, but we're always going to keep the degree to be the same. See, it doesn't depend on n. And the spectral expansion is the same. It doesn't depend on n. So of course, if you wanted a better spectral expansion, you can take just some small power of gn. Right? If I wanted like a quarter expander, I'll take a gn squared, and so on. So this is going to have constant degree. So now let's prove it. The proof is going to be just basically simple calculation using the zigzag theorem. So let's start with the base case. So what about G1? Well, with G1, so H is d-regular. So G1 is going to be d-squared regular because it's just, H squared, square the degree. And also H is going to be a 1 quarter expander. So G1 is going to be a 1/16 expander, and 1/16 is less than a half. So it's fine. G1 is fine. And it has d to the 4 nodes, because that's how we started with H. H has d to the 4 nodes. What about the general case? So what about Gn plus 1? Let's start with the degree. So remember, what was the degree of the zigzag? It just depended on the degree of H. It did not depend at all on the degree of G. Well, we know that we can actually do this zigzag because Gn squared, by induction, Gn has degree d squared. So Gn squared has degree, this graph, the degree here is d to the 4. And this one has d to the 4 nodes. So we can actually, the zigzag is well defined. And but then the degree of Gn plus 1 by the zigzag theorem is going to have degree, it's going to be the degree of H squared, which is going to be d to the 4, because we assume, sorry, will be d squared, because we assume H is d regular, so it will be d squared regular. And what's with the expansion? Well, it's going to be, let me use the alpha plus beta. So it's going to be at most expansion of Gn squared plus the expansion of H right? So let me have lambda. There's lambda here. So lambda gn plus 1 by the zigzag theorem is going to be at most lambda of gn squared plus lambda h, right? Because we're taking the zigzags of these two graphs. Well, what is a lambda of gn squared? It's just a lambda of gn squared plus lambda h. And we chose h to have be 1/4. So this is at most 1/4. For gn, it's going to be half, but when we square it again, we get 1/4. So overall, we get 1/2. So that's our calculation. So again, but this calculation doesn't really matter that much. I mean, it's good if you go over it, maybe later. But the whole point here is that we alternate these two operations: squaring a graph, which improves its eigenvalues but increases a degree, and zigzag, which decreases a degree and slightly hurts slightly has the eigenvalues. But if h is a good enough expander, it doesn't hurt you by too much. So overall, we win. Okay, so now the last bit of the puzzle is to prove this zigzag theorem. This is what we'll do in the next 30 minutes. But maybe before doing that, let me see if anybody has any questions. But maybe also make one comment is if you use this construction, what you're going to get is what's called a mildly explicit construction. If you remember, this is what Max discussed last time. So a mildly explicit, so this gives you just one comment. This is we're going to call the mildly explicit construction, which means that we can compute gn in time polynomial in the number of nodes of gn. So if I want to output the adjacency matrix, I can do it in polynomial time in the size of the output. But for some construction, what you really need is what's called a strongly explicit construction, which means that given a node, I want to find its neighbors in time polynomial in the side of the node, so polylogarithmic in the side of the graph. Now this construction as is doesn't give it, but there's a way to modify it. So it does give it. I mean, I won't discuss it here, but if you want, we briefly discuss this in the notes and refer to the paper which is being used. So just be aware that this construction can be modified to give you also a strongly explicit construction, but the way I define it here, it only gives you a mildly explicit construction. Okay. And again, for our applications, it won't make a difference, but for some applications, it does make a difference. So now again, last piece of the puzzle, we want to prove the zigzag theorem, or some slightly weakened version of it. So we're going to assume that G is going to have n nodes, capital D regular, and an alpha expander. H is going to have capital D node, small d degree, so small d regular, and beta expander. And we will show that the zigzag product is going to be alpha plus beta square expanded. So I promised you alpha plus beta, I give you something slightly worse. It doesn't make a difference. You can apply the same theorem as before if you want, with slightly different constants. Also, you can shade this beta squared if you do slightly better analysis at the end. So you'll see where we're sort of doing some type of slack analysis and how you can improve it. But it doesn't matter. Basically, if alpha and beta are small enough constants, that's going to be a small enough constant. That's all that you really need for this to work. Right? If they're both less than, let's say, 1/4, that's going to be less than 3/4 or something like that. That's enough. Then you square it a few times, you get something less than 1/4. Right? That's going to be our goal. How are we going to prove that? Well, in the only way we know how to prove expansion. We're going to bound the Rayleigh quotient, right? So let f be a function from the nodes. This zigzag. See, let me just use z here for the zigzag. So we want to keep writing. We're just going to Z. Z is the zigzag graph. V of Z. Wow. So it's going to be orthogonal 1. So it's sum over all the nodes is going to be 0. And we know that the eigenvalue of Z is smaller than the Rayleigh quotient. So it's going to be F transpose Z F over F transpose F. And also, just for simplicity, I will not, when I write Z here, I really mean, so I'll sort of, just so it's easier to write, so I'll use Z instead of AZ. So whenever I write a graph, or G or H, whenever I have a graph, here I would always mean the normalized adjacency metrics for this graph, so that I don't have to give it in AZ, AG, AH all the time. Okay. So this is what we want to do. And now, what's going to be the first? Right. So far, this is how this is the way we know how to bound. Eigenvalues. In fact, there are going to be absolute values here, but yeah. What can we say? First, the one thing we've seen is that okay, maybe do a picture before I do it. So remember, how does a graph look like? It's going to have this sort of small cloud of H, copies of H, and here's going to be the nodes. Right, and we're going to have, this is a replacement graph, right? And then our actual graph sort of like a path 3, length of path 3 here, that is step. And like a step. You go from here, I'm going to go here, here. That's going to be like one step. So it's going to be, so sort of it seems like the connectivity inside copies of H is determined by H, and the connectivities between copies of H is determined by G. So in order to utilize them, we're going to decompose F into 2 parts. A part of them, every local copy of H is just a local average, and the part that is orthogonal. This will allow us to decouple how H acts as an expander and how G acts as an expander. So let's define the following thing. So we're going to decompose F as F parallel plus F orthogonal. But now parallel is going to be inside each copy of H. So F parallel on a node VI. Remember, VI is a name of a node in the zigzag product, right? It's a node of G plus a name of an edge. It's just going to be 1 over capital D, small over all J in the J. Okay, so what is this parallel? So this is not a global parallel, so that's going to be 0. It's a local parallel part. So in every copy of H, I average the value of F there, and that's going to be F parallel. And then F orthogonal is going to be just whatever is left, right? F minus this part. So let's just write 2 things that we know about these things. So one thing I claim is that, well, F parallel is still orthogonal to 1 because it still should sum to 0. And it also locally, and it's still orthogonal with perp. And also locally, right? And also, this is also true in each, let's say, H cloud, right? If I take these vectors and restrict them to nodes inside H, they're still going to be orthogonal. Because this decomposition is basically done in a copy by copy way. Okay? That's going to be the first step. The next step is we're going to say, well, how do we define Z? Basically, we can 3 steps in the graph. So let's try to actually explicitly compute what does it mean to take a step in the zigzag graph. So remember, let's use green here. Remember that a step in the zigzag is the following thing. So 1, we take a step in the local copy of H, then we're going to take a step in G, then the best step is a step in H again, right? So this 3-step process to get an edge in the zigzag graph. Let's ask, what is a normalized adjacency matrix corresponding to each one of these steps? So let's take it. So in step 1, so the normalized, what is a normalized adjacency matrix for step 1? So I claim that is going to be basically a block matrix, because this step is just inside each local cloud of H, right? So I'm going to decompose it into these blocks of H. And in each one, we just take the step H. Right? We just, again, I'm using H for the normalized adjacency matrix of H. So I'm claiming that step 1, because it doesn't even move between clouds of H clouds, it's just a local step, right? Inside every local cloud of H, we take a random walk based on H. So it's just going to be this copy of the normalized adjacency matrix of H. And we just have this in a block diagonal matrix for every block. Right? So I sort of sort the nodes so that every cloud, the nodes in the first cloud, and then on the second cloud, and the third cloud, and so on. That's going to be the first step. And I'm going to give it this name. I'm going to call this HTL. So again, note it here. So each block is of size d by d, and in total we have n blocks. So this matrix is nd by nd. So is this first part clear? Why the first step, the local step in H, just acts locally in every copy of H, but because it doesn't move between copies of H, right? It's a local operation. What about the second step? Well, the second step just moves from, connects VI to some WJ, right? This is a GX, this is the G step. And it's deterministic, right? If I go from VI, I'm going to land in WJ. If I go from WJ, I'm going to land in VI. So this is going to be some permutation matrix. I'm going to call P. And for now, I know nothing about it. Just some global permutation matrix, because I can permute VI with WJ, or WJ with VI. Right? So just, there is no, with H, there was some mixing, right? Because H was like an expander. Here, there's no mixing. It's just it just permutes the nodes in the graph. It doesn't mix it in any way. So again, why? We go back to the picture up above. This step just goes from, let's say, if I go for use again green here, it just goes from this node always to this nodes, and vice versa. It doesn't have just one option or two. Just permutation. So just some permutation matrix. And what is step 3? Well, step 3 is the same as step 1, right? Because we said that the third step is just take another local step inside H. So we're gonna take a local step inside H, then it's a deterministic step based on G, and then another local step inside H. So overall, we can write the normalized adjacency matrix of the zigzag graph as follows: HTL P HTL. Okay, so let's stir this equation for a second, because that's a very important equation. It says the adjacency matrix of the zigzag graph corresponds to taking a local step inside each copy of H using this block diagonal matrix. Then take this deterministic step based on G, and then the local step in H again. And now let's plug in this equation of Z into the Rayleigh quotient. So again, we want to look on, now let's analyze the Rayleigh quotient. So what we're trying to analyze is the following thing. It's going to be, remember that F is orthogonal to 1, and we decompose as this sort of locally parallel plus locally orthogonal part. The locally parallel is just the average in every local cloud of H. So we're trying to analyze F transpose ZF over F transpose F, right? This is a Rayleigh quotient we're trying to analyze, showing it's not too big. And we just want to decompose this F as F parallel plus F orthogonal, and same in the numerator and denominator. That's going to be F parallel Z F parallel is transpose plus F orthogonal transpose Z F orthogonal plus twice F parallel Z F orthogonal divided by F parallel transpose F parallel plus F orthogonal transpose F orthogonal. So here what I use is just the fact that F parallel and F orthogonal are orthogonal to each other, the denominator, right? And it is symmetrical. F parallel Z F perpendicular is the same as its transpose, because Z is symmetrical. Okay. Now we want to finally start using this equation of Z to start to simplify things. Okay. So let's see what we know. So what do we know? Let's see. So remember Z. What can I tell about H tilde F parallel? Well, what does it look like? So here's H tilde, which is these local copies of H. And F parallel is some vector. In every block is going to be some constant. Maybe here it's always going to be some constant. This is going to be some constant C1, and in the second block it's going to be some constant C2, and so on, just a local average. So I'm claiming this is just going to be, because the all one vector with an eigenvector of H with eigenvalue 1 is going to stay the same. It's going to still be F parallel. So this will not change F parallel. F parallel is still going to be an eigenvector with eigenvalue 1. Because we're acting in each block, and in each block is just some parallel vector. Is this okay? So maybe part 1. Part 2, I'm claiming that if I look on its perpendicular part, it's just going to be determined by beta. Y. So let's see Y. So let's compute H tilde F perpendicular squared. So let's give this a name. Let's say now F perpendicular. And it's going to be these blocks. Again, the first block I'm going to call it F perpendicular 1, and the second block I will call F perpendicular 2, and so on. So what is this going to be? Well, because this is a block by block thing, this is just a sum of H F perpendicular. Oh, I put the perpendicular in the wrong place here. Sorry. I meant to write was the place. I meant to write was F perpendicular 1, F perpendicular 2, F perpendicular I squared, right? I from 1 to n. Just a block, this is L2 squared, this is sum of the squares. Each one of those, because H is a beta expander, and F perpendicular is orthogonal to the all one vector, is at most beta squared, I guess. Fi perpendicular squared, which is just beta squared F perpendicular squared. So again, this is just because this action is in a block by block way, and then every block is shrink by a factor of beta, the L2 norm. And then this is just a short calculation showing why this also shrinks the global L2 norm by a factor of beta. Okay, again, this is just the H, the local H action. So I claim that just these two things would allow us to already analyze many of the quantities here above. But let's analyze, for example, this term, the second term and the third term. What can you tell me about F perpendicular, H tilde, F perpendicular? This is one of the terms we want to analyze. Well, what do we know? We know that H tilde shrinks it by a factor of beta, right? Sorry, this is not what I meant to say was, sorry. Let's look on, sorry. Now I want to plug in Z to be H tilde P H tilde. So what are the quantities that we want to analyze? Let's look on F perpendicular transpose Z F perpendicular. That's one term. This is going to be F perpendicular transpose H tilde P H tilde F perpendicular, right? Now I know that this vector, its length is at most beta, the length of F perpendicular, right? Because it shrinks it. And the same holds for this one. This is also the same thing, same. And P, the permutation matrix. So it can only shrink vectors, it cannot increase the length of vectors, right? So overall, this is going to be smaller than beta squared F perpendicular squared. So we just have, because each H tilde shrinks the length of F perpendicular, and P is just a permutation matrix. Right, so it doesn't increase length. Right, so the length, for example, the length of this is the same thing, beta F perpendicular, and then just take the inner product, right? So this just pushes Schwarz. Yeah, so this is one part. The other parts, like whenever I have F perpendicular, basically I win. Like if I look on, like, for example, F parallel, Z, F perpendicular. What can we say about that? Well, it's the same thing. It's F parallel, H tilde, P, H tilde, F perpendicular. What do we know about this? Well, this is just going to be the same as F parallel, because so here I don't gain anything, because F parallel is an eigenvector with eigenvalue 1, H tilde. Here I shrink by length, so the length of this vector is smaller than beta perpendicular. And again, P is just doesn't increase length, so this overall is going to be beta, the length of F parallel, the length of F perpendicular. Okay. So this allows to control, just this by itself allows to control 2 of the 3 terms. We were able to control this term and this term. There's just one remaining term that we have to control, but we cannot just use H, which is the parallel part, right? The parallel part is invariant to H. Also, we didn't really use so far the fact that G is an expander. We should use it somewhere. Right? If G is not an expander, this should never work. But if G is not an expander, it's going to fail exactly because of parts that are constant in every H part, but are a bad eigenvalue for G. So somehow this first part should be handled by the G expansion. So let's analyze that last. So the last part we want to analyze is F parallel Z. F parallel. But remember, Z was H tilde P H tilde F parallel, and F parallel is invariant to H. This is just going to be the P part, right? Because H tilde F parallel is F parallel. So now finally we need to use the fact that G is an expander, and somehow we need to use this by this permutation matrix P. Now what's the idea? The idea here is that F parallel is constant on every H cloud, right? So if we have here again the picture from before, if we have these H clouds, then now it's going to be the same value in every H cloud. So to some extent, this is really just doing a walk inside G, because this it doesn't matter in which node of H you are. They're all the same. So what we want to do is to basically say this is actually the same as just making a step inside G, and G is an expander. Okay, so now let's do that. So that will be the last piece of the puzzle. So define, let's call this maybe G parallel of a node V to be F parallel of a node VI for any I, right? Because they're all the same. So G parallel is a function on on the nodes of G. And what is this? Let's see. What? And I'm claiming that if we can relate F parallel transpose P F parallel to this walk of G. Why? Let's just do the calculation. What is this going to be? So what is P? P connects all the nodes Vi that is adjacent to some Wj, the zigzag of F parallel Vi, F parallel Wj, right? This is what this permutation method does. Connects the node Vi to its neighbor Wj. Now the I and j are not important anymore, right? Because F parallel is constant on every H part. So this is just going to be the same as the sum of all the neighbors of G. This is in G. Of G parallel V, G parallel W. Right? And what is this? This is just going to be take the G parallel transpose times the unnormalized adjacency matrix of G. So D, G, G parallel. So notice this is just exactly doing the G parallel times the unnormalized adjacency matrix of the graph G times G parallel. Because we just sum over all possible edges. Because I'm using capital G to usually denote the normalized adjacency matrix, I just need to multiply by the degree to get the unnormalized adjacency matrix. Now, what do we know about G parallel? Let me put it here. Remember, we knew that F parallel was globally orthogonal to 1. Locally in every cloud it was constant, but because F was globally orthogonal to 1, then doing averages will still overall be orthogonal to 1. So we know that G parallel is also orthogonal to 1. So we can now finally apply the expansion of the graph capital G. So what do we know here? Well, that's going to be by expansion. That's going to be, so we can say that now what is the absolute value of F parallel transpose P F parallel? That's more the expansion of G, which we call alpha. Again, we have this capital D here, just this constant D that's going to be some scaling factor, it's going to disappear soon. Alpha G parallel squared. Right, just because G parallel is a vector, the function on the nodes of G, which is orthogonal to the all 1. So we can use the expansion of the big graph, capital G. And again, this is just going to be alpha F parallel squared. Because remember that F parallel has like D more nodes. So this capital D here, it's not, this is just a scaling factor, going from, because the number of nodes is different. It's not really, it's cancelled out. So overall, we got that this F parallel, because it's constant on every H cloud, it basically acts like acting on this graph G. So we'll gain the expansion of the graph G. So if you put all of this together, what do we get? So if we get it, if you're looking on this F transpose ZF over F transpose F. So this is going to be small. Remember, this was this parallel part, so there was this parallel part. The orthogonal part, and twice mixed part over and we should be transpose. Now we can bound. So the first part is what we just bound, right? It was alpha parallel squared. The second part was this perpendicular that we found 1 by beta squared. No F perpendicular squared. And the last part was just 2 beta parallel perpendicular. Right, so the second and third term we just use the expansion of H. The first part we use the expansion of G to bound them. And overall we normalized by the norm of F parallel squared plus the norm perpendicular. And I'm claiming that this is all going to be small. This is exactly what we wanted. The first part is at most alpha. The second part is at most beta squared. And the last part is at most beta. For the last part, so just as for the last part, why is it smaller than beta? Just because of the following equation, 2xy is smaller than x squared plus y squared. Right, so if x is the norm of f parallel and y is the norm of f perpendicular, then we just 2xy, and the denominator is x squared plus y squared. And this gave us exactly what we want. So this finishes the proof. So again, maybe just one thing about the whole, I mean, of course, there's some details here that maybe it's hard to grasp when you hear it for the first time, but you can go over the notes later and sort of see them again. But the main picture here is that, you know, we, in the analysis, we decompose to the parts that are constant in every h part and the parts orthogonal to them. The parts orthogonal to them are completely controlled by the h steps. G doesn't even help us. It doesn't hurt us. It doesn't help us. And the parts that are constant in every h part effectively translate to just a function on G. And then we can use the expansion of G to control that as well. And then there are some calculations to make sure it works. Also, another thing you see here, the way I sort of bounded this ratio is that I was sort of slack, right? Sort of, you can sort of improve the bounds here by doing it a bit more carefully, but you know, so you can get a better bound here if you work it out. But this is basically the analysis. That's it. This finishes the proof of the Zig-zag theorem. Questions? Yeah, I don't know if there are no questions. Means everything is clear or nothing is clear. Yeah, but one of those probably. Yeah, so please ask. Anybody has any questions on anything here? Or I guess also if you read it later and you have questions, you can ask them on Piazza. Maybe since we ran out of time, we can stop here for today. So basically, this was our last lecture on expanders. And next lecture on Thursday, we're going to start talking about high-dimensional expanders, which is going to be our main topic for the remainder of the course. And just a reminder, homework 3 is going to be, we're going to release it probably next Monday. It's going to be for 2 weeks after. It's going to be on high-dimensional expanders. All right. So I'm going to stop the recording and